Okay, so here goes my Newtonian mechanics and different coordinate systems video reassessment. I chose a problem from the list of homework problems you assigned us, a problem from the book. I chose problem 139 and then just digging right into it. The problem reads, a ball is thrown with initial speed v naught up an inclined plane. The plane is inclined at an angle phi above the horizontal, and the ball's initial velocity is at an angle theta above the plane. Choose axes with x measured up the slope, y normal to the slope, and z across it. Write down Newton's second law with these axes and find the ball's position as a function of time. Show that the ball lands at a distance r is equal to 2 v naught divided by g cosine squared phi times cosine theta plus phi. All right, getting right into my work. All right, so starting here, all right, first thing that the problem asks to do is come up with a new coordinate system. Basically, redraw the coordinate system where the x-axis is along the plane, the y-axis is normal to the plane, and the z-axis is across the plane. All right, so we're not going to really deal much with the z direction in this problem, but that's just what the problem asks, so that's what I drew. All right, so the first objective is to write down Newton's second law with these axes and find the ball's position as a function of time. I know that I needed the ball's position as a function of time. I would need my kinematic equation. All right, so first, to write down Newton's second law, basically just the sum of the forces in each direction is equal to mass times acceleration. I drew my free body diagram here, and basically I was able to come up with my acceleration in the x direction and my acceleration in the y direction. Okay, bam, that was the first thing. All right, so basically just finding the ball's position as a function of time. I started off with my basically displacement in the x direction. This is my kinematic equation. I need v naught times t plus 1/2 at squared. It's a lot of things in this equation that I don't have yet, but I'm going to find as we work through the problem. So first of all, my displacement in the x direction is going to equal to basically my initial velocity in the x direction, which is v naught cosine theta. I showed that on the first page, times t minus 1/2. This is my acceleration in the x direction, which I just found out from Newton's second law, times t squared. So there I have my displacement in the x direction. Okay, now this part was kind of difficult to understand, but stay with me here. All right, with my displacement in the y direction, even though we're launching the ball up the plane and at an angle, the ball is still going to land on the y-axis. So therefore, that makes our displacement in the y direction with respect to the plane equal to 0. So using that, we're able to find our time of flight of the ball. Okay, so basically what I did right here is I set my y displacement equal to 0, and then with that I divided out t in order to, and then once I did that, this t squared turned into just a t. This t over here canceled out, and therefore I was able to solve this equation for t, and that's why I got basically t is equal to v naught sine theta divided by 1/2 g cosine theta, and that is my time of flight of the ball, and that we're going to be able to plug that into the displacement of x direction equation, because no matter what, if that's the time of the flight of the ball, then that doesn't change. That's t. That is our t for the equation. So basically the next step was to go back to our displacement in x direction, which is what the problem is asking me to find. The problem is asking me to prove that the range, which is the displacement in the x direction, is equal to what it said on the first page. So here I'm just plugging in basically back to my displacement for x equation. I have 1/2 ax t squared plus v naught x t, or basically v naught x t plus 1/2 ax t squared, which is just my acceleration in the x direction, my time of flight, and then my initial velocity in the x direction. Plugging in those things like I just found. See, this is my v naught x. This is my time of flight for the ball, plus 1/2. This is my acceleration in the x direction, and this is my time of flight of the ball squared. And the rest is just algebra, just going through the problem, exactly plugging in these things, trying to, simplify, because the thing that the problem asked you to do was not only find the range, but it gave you the range. It's just saying prove that this is the range. So basically that's what I'm doing. And here I ran into some bumps in the road. So basically this is the range that they ask you to prove. Say prove this is the range. And here I got to right here. And this is basically a difficult trig problem. I know that it works out though because I plugged the equation into my computer algebra system on my TI Inspire calculator, and I did get this range up here. So I'm sure if I plugged in some values, I would get the same thing. But working out the algebra, it kind of got a little tricky. But I do know that this is the trigonometric identity that I'll need to use in order to solve for this. So I checked out that this is the equation for the range. I did prove that to a certain extent without this trig, and that's pretty much it. All right. Thank you.